Okay, welcome to the fifth gas processing tutorial. In tutorial 4, what we did was to look at introducing transient simulations in OLGA, and we looked at building cases for shutdown and restart in both the simple case that we have displayed right here, and also in a more complicated multi-well case. What we're going to be doing in tutorial 5 is taking a look at another transient phenomenon in OLGA, which is related to hydrate formation. Now, first things first, what are hydrates? Well, basically, you can think of them as ice that forms at high temperatures. So you might get hydrates forming up to 20 degrees C in your pipeline if the pressure is high enough. And you can imagine that if you have these solid ice-like particles forming within your pipeline, this can cause some serious problems for you. So when we're simulating hydrates in OLGA, we again have to make use of both Multiflash and OLGA. So if we open up Multiflash and we open up our black oil with water, which is the fluid file associated with this simple case here, what we're going to go ahead and do quickly is to take a look at where it is that hydrates are actually going to form. And what we need to do whenever we deal with hydrate formation in Multiflash and OLGA is to change the model. So we go Select, Model Set, click on the Hydrates tab up here, and we use the CPA InfoChem model. We select the phases that we want to be looking at. Now typically it'll be looking at Hydrate 2. In very specific circumstances you can look at Hydrate 1. And the viscosity models here, let's just use Peterson, and we'll set these to mixing rules as we have done previously. I should note that these transport properties are going to be much less important when we're looking purely at hydrate formation, and we are largely concerned only with the thermodynamic or phase calculations done by the CPA InfoChem model. So we press Define Model, there we go, and now what we can go ahead and do is to do some hydrate calculations. So the first thing we'll do is to just change our units. Temperatures in degrees C, and let's deal with pressure in bar. Okay, so let's take a look at what happens at 15 degrees C if we have a pressure of 100 bar. So we can do a PT flash, and you can see the phases that we have available: oil, water, and there is hydrate present. So what this tells us is that at these conditions, yes, we have some sort of hydrate phase that is going to form. What we can also see is that the components that are incorporated into this hydrate phase are only these lighter hydrocarbons, so methane, ethane, propane, and N-butane. And of course we have our water down here, but none of these larger hydrocarbons can actually fit within the hydrate structure. So this is one condition at which hydrate will form. If we want to see more generally where hydrate is going to form, let's press this Phase Envelopes for Solids button up here. Now this brings up our overall phase envelopes, and it does calculations for a large number of the different phase envelopes that we have available. So you can see in blue here, there's the VLE. We have water dew point here, and then we have our hydrate and ice formation squeezed in here. Now, if we want to take a look more closely at these curves, what we can do is to write to Excel, and this will actually just bring up a new case of Excel. Okay, so we can then also change the axis boundaries. So let's look at it from minus 20 degrees up to 50 degrees, and let's decrease these units here so that we actually get something showing up. Okay. So what we can see is we have our ice formation line below 0 degrees, as we'd expect. We have our VLE curve in here, and we have our hydrate formation curve. So you can see that once we get up to very high pressures, we can get hydrate formation even around 30 degrees C. Now, these are extreme pressures, and we're more likely to be dealing with this sort of range here. So basically, hydrates, like ice, form at the low temperatures, and in the case of hydrates, at high pressures. So this region in here is going to be our hydrate formation region. And when we heat up our pipeline, or we decrease our pressure, this region is where hydrates are unstable. So you can see immediately that Multiflash can be used to work out where hydrates are going to form. But if you want to work out how fast those hydrates are going to form, that's where we need to turn to a tool like OLGA. So if we're going to be looking at hydrates in OLGA, what we need to once again do through Multiflash is click Table, OLGA, and now what we want to do is to actually change the fluid ID that we are using. So rather than tutorial black oil, let's call this tutorial black oil hydrates. There we go. And this can be our hydrate fluid file. And now what we have to do is to also create a second section here, which is going to be our hydrate formation file. So you can see, rather than a .tab, this is a .hide file. So this can be black oil hydrate curve .hide. And again, we need to give this some sort of pressure range. So let's go from 1 bar up to 200 bar, why not? 50 points. Temperature can be minus, let's say, 20 degrees, up to 150 degrees, with again 50 points. So what we can go ahead and do is to calculate our tables. There we go. So these have both been created again in Multiflash. And what we can do then is to add these into OLGA. The way we do this is to again jump over to OLGA. And what we'll be doing is looking at this simpler case, and we'll just duplicate our tutorial 3 start. And we will call this tutorial 5 start. There we go. Alright, and this is what we'll be editing from now on. Okay, so in order to add our hydrate curves, what we do is expand this, take a look in library, and in fact right click, add hydrate curve here. There we go. So this can be set to take a value from file, or we could enter a series of P&T manually. Okay, so we can select our hydrate file here, and this is the .hide file that we just created. So black oil hydrate curve.hide, you can open that. And so now whenever OLGA wants to work out when hydrates are going to form, it's going to look at this particular file here. So the other thing we just have to make sure of is that our temperature and our pressure are in units of C and bar, because when Multiflash generates this file, it's going to create a file with units that are Celsius and bar, so we have to let OLGA know that this is what is going on. So we click OK, and there we go. So we've now specified what that curve looks like and the correct units for it. Alright, so this tells OLGA about the thermodynamics of where hydrate can form, but we also have to tell OLGA where it is that we would like it to actually check for hydrate formation. So what we're going to do is to take a look at our flow components here, and as we saw previously from those equilibrium curves, we're going to start getting hydrate formation where our temperatures decrease. So typically this is going to be in the flow line and maybe also in the riser. So what we are going to go ahead and do is to right click on our flow line and add. And we're going to look at flow assurance models. And then we have 3 different sections in here. Hydrate check, so this is going to see if hydrates form. Hydrate kinetics tells us something about how fast hydrate is going to form. And our hydrate options is going to have some sort of advanced model options for hydrate formation in it as well. So we want to add hydrate check. And we also want to add the other 2 here. So flow assurance models, hydrate kinetics, add flow assurance models, hydrate options. There we go. So we have these 3 things here active. So what we're going to do now is to say in our hydrate check, this is basically a reference to that hydrate curve that we created previously. So you can see it requires a hydrate curve. And this is our HYDE1 hydrate curve here. Okay, and you can see that's the name given up here. We can take a look at our kinetics, and it needs a model type. So what we're going to be using is the Kinetic model. So this is the Bishnoi or Turner's model, effectively, for hydrate formation. And you can see then we have a number of different options here. So we want to be using, yes, structure 2 hydrate. This is the subcooling at which hydrate is first going to begin to form, and that's 3.6 Kelvin, which is an industry heuristic. So fluid dispersion, if we take a look here, this is going to force all of the oil or water to be dispersed in the water or oil, depending on the inversion point. So basically, this kinetic model does indeed assume full dispersion of usually water within the oil phase, so we'll turn that on. And our final one then is to take a look at these sea oil and sea water. And as you can see here, this is basically a weighting factor to control how fast is the hydrate going to travel relative to these phases. So we want to set this to 1, so that's going to travel along with the water phase. So our final section here is our hydrate options. And what we can do with these is to just leave them for now at the default settings that they have in here. So these are kinetic scaling factors for the kinetic equation. Mean diameter is going to be the droplet size that is used when calculating the number of droplets in a given control volume, and therefore working out what the area of that is for reactions. Our fat traction, this is an expression of the interparticle force that's going to be cohering hydrates together. You can see 50 millinewton per meter. Okay, so we have these 3 flow assurance models for our flow line. What we should be able to do is to copy these into our riser as well. So hydrate check, hydrate kinetics, hydrate options, and we can just double check that these settings are put in here correctly. So again, we're looking at our hyd 1, our hydrate kinetic settings are maintained, and our hydrate options, we didn't actually make any changes to those at the present time. Okay, now one final thing that we're going to do is to just change the resolution of our simulation slightly. So when we were doing our simple calculations and we just wanted to know approximately how things were moving, it was okay to use a relatively coarse simulation. You can see here we have 5 kilometer nodes or control volumes. What we're going to do is to increase the resolution of our simulation, and we're now going to have 1 kilometer nodes. So we can close this and say okay, and we can probably do something similar in the riser here. Okay, so in the riser you can see that we already have sections which are only 20 meters long, so that's going to be perfectly okay for the moment. Okay, so we have hydrate formation set up, but as with everything in OLGA, what we need to also do is to tell it what we would actually like it to record in terms of its outputs. So in our profile data, let's go and take a look at searching hydrate. Okay, so what have we here? The hydrate volume fraction, physically how much hydrate is in the system, that's going to be important for us. And also we want to take a look at the hydrate formation temperature, so hyd Tm in here. Okay, so we'll just take a look at these 2 parameters for now, so we press OK. Now they're going to be tracked in our flow line. Similarly in our riser, we'd like to be taking a look at these parameters. Again, hydrate, DE hyd, and hyd Tm. Okay. Now what we can do with these parameters being tracked is to press run batch. Now once again I should note that we've just increased by a factor of 5 the number of nodes that we have to solve in our flow line, so that's going to increase the amount of time this takes to solve. You should also note that whenever you're looking at hydrate formation in OLGA, that also slows things down significantly. Okay, so with that completed, we can begin to take a look at some of our results. So again, we'll just create a profile plot, and we are interested firstly in what's happening with the flow line. Let's take a look at temperature, hydrate equilibrium temperature, and the amount of hydrate that is formed, and we'll also take a look at the pressure in here. And you can see that at the start of the simulation, nothing particularly interesting has happened. But as soon as we begin to bring that forward, we can begin to see the kinetic aspect of OLGA at play. So remember, this is our initial steady state condition that the steady state preprocessor built for us. And once that's converged, OLGA then turns on its hydrate formation, and this is a kinetic phenomenon, so it changes as our simulation progresses. Now, what can we see in this particular plot? Well, our red is our hydrate equilibrium temperature, which is dependent on our pressure. Our green is our system temperature, and the black is the amount of hydrate that is formed as a volume fraction. What you can see is that as the fluid begins to cool within the flow line, it dips down to 3.6 Kelvin, which was our specified subcooling, below the equilibrium temperature, and then hydrate begins to form. Now, hydrate formation is an exothermic process, so what happens here is that the heat released by hydrate formation immediately bumps our temperature up to the equilibrium temperature. And you can see then that because these two track together, what we have is a heat transport limited case of hydrate formation here. Now, despite this, we still have rather a large amount of hydrate which has formed. You can see at the end here, this is our hydrate volume fraction, which is 0.35. So that means that 36% up here of the pipeline is hydrate. So you can imagine that when you have so much hydrate within the system, you can begin to run into problems. And this brings us to the next part of the tutorial, which is looking at various strategies for managing or inhibiting hydrate formation. So the first one that we're going to take a look at is the idea of insulating our pipeline. Now we can do this by tweaking our heat transfer module settings for our insulation. So our initial, more or less, uninsulated pipeline was simulated by this heat transfer coefficient of 23-ish watts per meter squared per Kelvin. Now let's simulate some sort of moderate insulation and see what that result changes to. So all we have to do is to change this U value, and we can verify our simulation and run a batch process. Okay, so this has finished, and what we can go ahead and do is to see what the effect of that insulation on the flow line was. So again, we go back to our profile plot, and let's just press reload. And what you can see is that there is a very significant difference once we have this insulation in place. Now, we've managed to retain heat for a much longer distance along our flow line. And what that means is that hydrate has been thermodynamically unstable up until we get to about the 35 kilometer mark here. And you can see that rather than having 35% hydrate within our system, we now have a maximum of 2%. So that really is a significant difference. And what you might be able to see is that with a little bit more insulation, at steady state, you could completely prevent hydrate formation within this particular line. And all that you would have to worry then about would be what happens when you're starting up your line, and that comes back to the sort of transient shutdown and restart calculations that we looked at last week in tutorial 4. Now in effect what we're doing with this insulation is to use the natural energy of the system in order to prevent hydrate formation, by making it thermodynamically impossible for it to form in this initial region. Now, where insulation isn't sufficient to do this, there is another class of inhibition strategy known as dosing with thermodynamic hydrate inhibitors, such as methanol or monoethylene glycol. Now we can also look at these THIs in OLGA and Multiflash. And the way we do that is to go back to Multiflash and change the way that our fluid is defined. So once again, we have here in Multiflash that case that we used to generate the hydrate curve previously. And what we can do here is to see about adding some sort of inhibitor to the system. So we can go to Tools and Inhibitor Calculator. And you can see what we've brought up here is a little window which says we have this much water in the system. And we would like to add some sort of inhibitor. And you can see the way that this is determined is it's the weight percent at the moment of water plus inhibitor. So let's go ahead and use methanol, and let's say we'll use 20% by mass methanol dosed into our system. So if we press add, then you can see that Multiflash wants to add methanol to the system, and this is how much methanol it wants to add. So that is fine. We can close this. We can take a look in our compositions tab, scroll down to the bottom, and we can see that now we have methanol in the system. So what we can do is to once again look at what phases we have present. And you can see now this hydrate curve has been shifted. And we can write this to Excel. And once this has been put in Excel, what we can actually do is to lay on top of our previous simulation for our undosed fluid. So if we delete these other curves here, and we again zoom in, so let's take a look from minus 20 degrees up to 50 degrees. So we can see that as we've added the methanol, it's gone and shifted the hydrate equilibrium curve towards a lower value. There we go. So rather than 22 degrees at 300 bar, we are now down to 11 degrees. Now, so if you can get a cooling curve from OLGA, you can lay that on top of this PT plot, and you can very quickly, by adding more methanol or MEG to Multiflash, see how much is going to be required in order to fully inhibit your system. So now what we're going to do is to just go ahead and add this methanol to our hydrate equilibrium calculations and see how that affects hydrate formation in OLGA. So again, we go Table, OLGA, and what we want to do is to create a new table file. So rather than overriding black oil hydrate curve, this is black oil hydrate curve with 20 methanol. Okay, and we can keep our table values as they were previously, and once again calculate table. Now it's asking us if we want to override our PVT file, but effectively we wind up throwing this PVT file away for hydrate calculations. So we can say yes, that's fine. And there we go. We've now calculated our new table. So we can go back to OLGA. And now what we have to do is within our library, look at our hydrate curve, and to change this hydrate file. And we can change that now to black oil hydrate curve with 20 methanol. Okay. And what we're going to do as part of this demonstration is also to just change that insulation back to 4 BTU per foot squared per hour per Fahrenheit. There we go. And let's rerun the simulation. Alright, so let's take a look at what this looks like now. So let's note that the initial hydrate temperature is down here around about 10 degrees C, and in fact, there we go, 13 degrees C along the pipeline. As we refresh that now, we can see that that has dropped to 2 degrees C. And what you can see all along the pipeline here is that that's actually entirely below the temperature that the flow line reaches. And the reason for that is that the seafloor temperature is around about 4 degrees C. So you can see if you were to dump 20% methanol into your system, then you could prevent hydrate formation along the pipeline. Now that would require continuous injection of methanol. So what you could potentially do instead would be to look at starting to blend these strategies together. Maybe you could insulate in order to prevent hydrate formation at steady state, and you could inject MEG on startup in order to make sure that no hydrate forms during that restart phase. So what we can also go ahead and do is to just decrease that amount of MEG slightly and see what the effect is on hydrate formation once again. So if we go back into Multiflash, let us just halve the amount of methanol that's in there. So this is now going to be about 10 weight % methanol in the system. And again, we go to Table, OLGA, we can browse. Let us call this with 10 methanol. Okay. We'll keep the same bounds on our table, calculate, overwrite the PVT, and go into OLGA once more. Change that hydrate curve to only 10 weight percent methanol, and just rerun the simulation. Okay, so the simulation is finished. Now let's go ahead and take a look how that affects our profile plot. So if we again reload this, interestingly, what we see here is that we still don't actually have any hydrate formation. Now, if we go to View and Track Values, if our hydrate formation temperature is 7.1 degrees, then in order for hydrate to form, we would have to get down to approximately 3.5 Celsius. So what we can see is that because of that subcooling condition that we put in, this 10% of methanol is still enough to prevent hydrate formation in the system. Now, this is, in some sense, a limitation of the model in that hydrate formation is a stochastic process, and you can't necessarily just assume that if you have less than 3.6 Kelvin subcooling, you aren't going to get any hydrate formation. So what we'll go ahead and do now is to, once again, just slightly decrease that quantity of methanol in the system to see what happens when we have some hydrate formation in the system, and also some thermodynamic inhibitor. So within Multiflash, we previously had 33 moles of methanol, so let's change that to 17. And again, table, OLGA, let's change this now to 5 methanol. Okay, open that. We can calculate our table and go back to OLGA. Change that hydrate curve once more to 5 methanol, open, and let's run one final simulation with thermodynamic inhibitor. Okay, so our 5% methanol simulation is finished. Let's go ahead and refresh that plot one more time. And what we can see here is that once again, we wind up at that thermally limited case. So hydrate has begun to form, despite the fact that our equilibrium temperature has been reduced slightly. And as soon as it does form, it thermally limits and we get some sort of hydrate formation. Now what you should notice is that we actually do have less hydrate formation overall in this system. In fact, we have 22% at the end of the flow line, as opposed to the 35% that we had in the completely uninhibited case. And what this tells us is that because we have added some sort of THI to the system, the kinetic driving force for hydrate formation has actually been reduced. And so therefore, even though we do get some hydrate formation, we get less hydrate formation. Okay, so we've taken a look at the use of thermodynamic inhibitors. Now, these are more traditional methods of preventing hydrate formation that are used by the industry. But there are also other methods which are typically called low-dosage hydrate inhibitors. So what we're going to go ahead and do is to switch back to our normal hydrate curve, and we're going to investigate what the effects are of using some of these alternative dosing strategies. Okay, so the first of these low-dosage hydrate inhibitors that we're going to take a look at simulating are called kinetic hydrate inhibitors. Now, what these basically try and do is to either decrease the growth rate of hydrate formation and or, more commonly, to increase the required subcooling for hydrate formation. So what they aim to do is to prevent hydrate formation over the residence time of fluid in the pipeline. So what that means is that if you have some oil coming from the inlet of your pipeline, by the time hydrate has begun to nucleate, it's already exited the pipeline, and so therefore hydrate formation within the pipeline itself is not a problem. So the way that we can go ahead and simulate that within OLGA is to have a play with some of our hydrate options. Now specifically, if we take a look at our hydrate kinetics model, we have that idea of our subcooling. Now typically, the subcooling for these KHIs are thought to be effective up to maybe 12 or 13 Kelvin. Okay, so let's go ahead and type in a subcooling of 13 degrees C or 13 Kelvin, same thing. Now, one important thing to note with the use of KHIs is that we have also specified that we can form hydrates within the riser as well. So what we really should be doing is also changing the properties in our riser. So let's go ahead and set both of these things to 13 Kelvin. And then what we can go ahead and do is to run a simulation. Okay, so the simulation is complete. What we can do is to just quickly recreate that profile plot in the flow line. So we look at temperature, hydrate equilibrium temperature, quantity of hydrate, and that should be good. Okay, so what we can see here is in the case of this kinetic inhibitor, we have absolutely no hydrate formation in the flow line at all. So you'll note that this is similar in terms of the way we simulate it to adding a thermodynamic inhibitor to the system. But there are some important physical differences with kinetic hydrate inhibitors that we also have to consider. So what this result shows us is that at a steady state condition, yes, the system will be inhibited by using these KHIs. But what we also need to consider is that, once again, hydrate formation is a stochastic process. And the longer that we leave fluid at a low temperature, the more likely it is that some sort of nucleation event is going to occur. And then in the case of KHIs, typically the hydrate will go ahead and grow as if there is no inhibition there at all. So, this can potentially have a number of rather serious implications when you're looking at restart. So if you've got a shut-in case where everything is equilibrated with the sea floor, and that's left for days or weeks, then it's likely you're going to get some sort of hydrate nucleation within the pipeline. And then, if you restart your flow line with that nucleation already there, the kinetic inhibitor that you have within the system is not going to be particularly useful. So it means that you should really, if you are considering the use of kinetic inhibitors, think about these special cases such as shutdown restart. Alright, so there's one more class of low dosage hydrate inhibitors that we're going to take a look at, and these are known as anti-agglomerants. Now, the way that anti-agglomerants should work is basically to interfere with the way that hydrate particles stick together. So the principle in this case is that we allow hydrates to form, but we prevent them from sticking and therefore prevent any of these larger blockages from occurring. So the way that we can simulate that in OLGA is to take a look at our hydrate options. Now the first thing that we should do is set our subcooling back to 3.6 Celsius, or more correctly, to 6.5 Fahrenheit. Okay, so we can come now into our hydrate options, and the way that these anti-agglomerants are supposed to work is to reduce the force of adhesion between hydrate particles. So the way that we can simulate that within OLGA is to affect this fat traction parameter that we can see here. Now, its standard value with no AA added is 50 millinewton per meter, but if we were to dose in an ideal non-dispersing anti-agglomerant, then we might be able to reduce this down to, say, 1 millinewton per meter. Now, before we go ahead and rerun our simulation, we need to look at one more thing. Now, if our anti-agglomerant should not significantly affect the amount of hydrate that's formed, then the current figures that we're looking at in terms of our equilibrium temperature and our quantity of hydrate formed are not going to really tell us much. So what we can do instead is to take a look at another parameter that we're able to see in our outputs. So if we take a look at our profile data and we open this up, what we're interested in looking at is the hydrate slurry viscosity ratio, vis ratio. So this basically tells us how viscous the hydrate slurry is going to become as a result of all of those solid particles moving around in it. And so while we're tracking this variable here, we can then go ahead and run our simulation. So this viscosity ratio, it's effectively the ratio of the slurry viscosity with hydrate formation to the base oil viscosity. So when this value is 1, then we should see nice flow without any hydrate formation. But with hydrate formation, this ratio can increase significantly. And OLGA has a hard cap of 4,000 for its viscosity ratio, or its relative viscosity, coded into it. Okay, so this simulation with AAs has now been run. And if we take a look at our profile plot, we can refresh this, and you can see, yes, we still have that 36% hydrate fraction at the end of the flow line. What we can do then is to add in our vis ratio to this plot. We just add it down the bottom here, and we press OK. Now we can see that this gets up to a value of about 10, I believe. There we go, a value of about 10 at the end of the pipeline here. So what this basically means is that our fluid that's flowing through here is about 10 times as viscous as that base slurry. Now what we can do here is to compare that by running yet another simulation with what the value would be if we did not add that anti-agglomerant at all. So we can go ahead and do that by changing the that traction back up to 50 millinewton per meter, and once more running that simulation. Okay, so this final simulation is done. So our base case looks like this. And you can see that without any anti-agglomerant in the system, we have a vis ratio that approaches 100. So what this effectively means is that by adding an anti-agglomerant to the system, it's going to be 10 times easier for our oil and gas to be produced. Now, is that going to be sufficient hydrate management strategy? Well, potentially it requires some more experiments to be run. And you also have to think about the effect on flow rate of having a fluid which is now 10 times more viscous than the original. Now, interestingly, if you look at the flow rate outputs from OLGA, you'll see that it doesn't take into account this effect on flow rate of the increased viscosity. So this is something that needs to be kept in mind when you're looking at your OLGA simulations. Alright, so I think that about wraps it up for this tutorial. What we've gone and done is to look at how to add hydrates into OLGA and to integrate that with Multiflash. And we've had a look at some hydrate formation just in the flow line of our system. Be aware that when you're looking at hydrate formation in OLGA, you actually have to define which components are allowed to form hydrate. Now in this case, what we did was to say that we can form hydrate in the flow line and the riser, but we only showed inhibition strategies within the flow line itself. Now, if you're running design cases, then you of course need to take a look at how hydrate forms throughout your entire system. Now, we should also note that we were only really looking at the steady state solution, and the transient component was just the rate at which hydrate was allowed to form. So, when you're considering transient cases, what you might be interested in is, for example, the concept of a cold restart. And some of these different mitigation strategies are going to perform very differently in a cold restart to how they would under these ideal steady state conditions. Alright, so in the next tutorial, which will be tutorial 6 and our final tutorial, we'll take a look at some additional solids formation in the form of wax dropout. And what we'll do there is to combine OLGA and Multiflash in order to predict how much wax is going to drop out of our system. And ultimately, what we might wind up doing is building an Excel spreadsheet in order to help us to understand how this process works.